Welcome to our section on initialization with water saturation array. The focus of this recording is the transition between the saturation height function when you have been given the parameters and how you can honor the water saturation array in initializing your reservoir simulation model. Before I dive into the detail of this, I would just like to quickly remind us the log evaluation workflow, which is usually a very fast and practical method for identifying the reservoir quality and the hydrocarbon potential from well logs. And we usually start this with the gamma ray log. So you can see the gamma ray log here to identify the reservoir interval. So we just want to understand our sand path just by looking at the gamma ray values, which typically indicates whether we have clean sand or we have shale or dirty sand, as the case may be, depending on the nature of the signature. Of course, the clean sand will have very low gamma ray, low radioactive elements in the clean sand, whereas the shale will have high gamma ray value. Once we have identified the potential reservoir interval, we now need to identify the potential hydrocarbon bearing zone within this interval. So we can use the neutron and the density log in order to achieve this. And what we are looking at here is the neutron log. Of course, it increases this way, while the density increases the other way around. So what you have seen here in the shale is high neutron log and high density. But the moment these logs encounter the gas interval or the gas zone, there is the crossover. And this crossover is as a result of the decrease in the density, which we have seen here because of the presence of the gas within the pulse, and also the decrease in the neutron log. The decrease in the neutron log is associated with the fact that the two measures the hydrocarbon concentration in the formation. Water and oil contain lots of hydrogen, so high neutral porosity reading as a result of that one. But for the gas, contains much less hydrogen per unit volume in the rock, and that is what is actually leading to the low neutral porosity log. So the way you need to visualize this is that when the tool actually enters a gas-bearing interval, it thinks there is a less pore fluid present, so it reports a lower apparent porosity than the true porosity of the system. But the main point here is this crossover happens whenever there is gas cap or free gas in the system, and it collapses back just the moment it enters into the liquid zone. The nature of the liquid, of course, could be oil, could be water, but we will try to do a better job with a different log in the next track. From this interpretation, I can say that our GOC could be somewhere here, but definitely we do have the gas cap in this reservoir at the top of the formation here of the sand. And once we have identified the fluid type, that is the gas, that there is gas in the system, then we can evaluate the porosity across the water, oil, and gas zones. This will help us to determine the storage capacity of the reservoir. And the final step uses the resistivity log basically to identify a water-bearing interval so that we can separate the oil from the water. Or better still, let me say, the hydrocarbon from the water. We know that the hydrocarbon, whether gas or oil, do have high resistivity, while water, being conductive, more conductive than the hydrocarbon, will have lower resistivity readings, which is what we see here. So the moment we see the resistivity value dropping to the lower value, we know that we've reached the oil-water contact. Okay, so what we have seen here, the workflow is straightforward. It helps to identify the reservoir with the gamma ray, that is the sandpack. Then through the help of the neutron and density logs, we're able to identify the fluid type, the gas. We're also able to estimate the porosity, and we're able to calculate eventually the resistivity and identify the water zone. And finally, we can also use this resistivity to calculate the water saturation using Arch's equation. And this provides a rapid first pass assessment of reservoir quality and hydrocarbon potential for us. Another important data that we can actually use here is our RFT or MDT. And this is the distributed pressure measurement along the wellbore or the bore for our well. So, and we can see that the gas gradients, these measurements are influenced by the type of the fluid in the system. So this is controlled by the gas gradient, and this is the oil gradient, and this is the water gradient. And we can see the interception, which should correspond to the oil-water contact, and same interpretation for the GOC. One thing from the practical standpoint that I need to highlight is the fact that the OWC from the logs and from the pressure measurements might not coincide completely. And this leads to the concept of the oil dam tool, which I will discuss in another recording. Nevertheless, whatever difference that may exist between them will actually help to define the uncertainty envelope in our oil-water contact. Once we have the porosity log established, it's also important to have the permeability. Since there is no log to estimate permeability, we tend to rely on the core data in order to be able to make a plot of the porosity versus permeability. And as you expect, we see a clear positive trend in these plots. We see that as porosity increases, permeability also increases as well. So the way to look at it is that the rocks with the more pore space typically has better pore connectivity, especially if you are looking at sandstone system, which will allow fluids to move more freely. However, I would like to point our attention to the scatter in the data. That is, for the same porosity value, permeability can vary significantly. So if you take 0.3, you can see that the permeability value varies significantly. This tells us that the permeability is influenced not only by the amount of the pore space, not only by the porosity, but also by other factors, such as the pore throat size, the grade sorting, the cementation, and even the rock texture. And that is why we have this cloud of data around the porosity from the permeability, because it is not just influenced by the pore space in the rock. The key takeaway here is that the core porosity permeability cross plots help, the plots help us significantly to quantify the relationship between the storage capacity and the flow capacity, which provides a fundamental input into our reservoir simulation and production forecasting. And once so far, we already have the structure. Let's believe that the geophysicists, they've done the seismic interpretation, they've understood the structure of the formation, the horizons, the discontinuity in the system, which corresponds to the faults in our reservoir. If there is any displacement and all that, it will impact the geometry of the reservoir, so the structure of the reservoir. And we have the logs, the porosity logs, and we also have the permeability. We have facies, we have all kinds of logs that will help us to understand the properties in our reservoir. And we upscale them, we populate them using geostatistical approach. Then we want to really see the behavior, because most of these rock samples, they are deposited at different times. There are a lot of processes, geological processes that have affected them, affected the connectivity as well. So it is important to really put them in what we call the rock typing, to really understand different rock types that we have. One of the methods that we use is what we call the flow zone indicator, FZI, which is a method that groups rock based on their flow behavior rather than maybe porosity or permeability alone. And the calculation starts with the reservoir quality index, as we can see, which is equals to 0.014 multiplied by the square root of permeability divided by the porosity. And once we establish that, the next thing is, of course, to calculate the normalized porosity. The normalized porosity is given by the porosity of the system divided by 1 minus the porosity, which accounts for the pore structure of the rock, while the reservoir quality index combines both the permeability and the porosity to represent the rock ability to transmit the fluids. Then we move on to the calculation of the flow zone indicator, which is simply the ratio of the reservoir quality index to the normalized porosity. So the physical interpretation of this is that the FZI actually reflects the quality and the connectivity of the pore system. So the rocks with, say, larger, I would say, pore throats, who have better connectivity, will have that's larger pore throats, better connectivity, they will have higher FZI values. That is the flow zone indicator value, and therefore better flow performance. And that is the implication. So we're trying to understand different rock types so that we can assign the appropriate relative permeability that will help us to be able to mimic their flow behavior better, instead of assigning maybe a single relative permeability or a wrong relative permeability to the wrong part of the reservoir. So once the FZI is calculated, then we classify the reservoir into different rock types by the, I would say, FZI cut-offs, which we have on the slide. For instance, we're saying that the rock type 1, if the FZI is greater than, if FZI is greater than 6.3, and the rock type 2, if our FZI is between 4.3 and 6.3, and so on and so forth. So in this case, we have 6 rock types, basically, okay? And finally, these rock types are assigned to SAT in terms of Eclipse keywords, basically. But it really doesn't matter the name you call it, as long as you assign it. It's just to help to identify which cell in your model should use which particular relative permeability and capillary functions in our simulation model. This slide shows how we model the capillary pressure and the initial water saturation using the saturation height function that I previously discussed with us in the last recording. The starting point in this case is the capillary pressure equation, which relates the pressure difference, the capillary pressure itself between the oil and water, to the height above free water level, as well as the density difference, which is between the oil and the water in the case of the oil-water system, and also related to the interfacial tension and the wettability of the system, measured by the contact angle in this case. And once we calculate the capillary pressure, so this is done for each cell in the model. So I just want you to imagine that your petrophysicist has given your geomodeler all the parameters of the saturation height modeling, let's say from Brooks-Corey relationship, that is SWIR, PCE, that's the entry pressure, and lambda, which is the pore size distribution index that we have, or N, which is the inverse of the lambda, as the case may be. Those parameters, they are actually parameters that you must have regressed or you must have calibrated them with your actual capillary pressure data in a software like TechLog that you use to model the saturation height function. That means that you must have matched them with your data. And please refer to my last recording on how that is done. So you know all the parameters in this case, and in the case of Brooks-Corey, and the capillary pressure is calculated per each cell in the model as a result of the height above free water level. Because once you use geometrical property in Petri, for instance, to calculate the height above the free water level, that each of the cells, their position relative to the free water level, you can actually calculate the capillary pressure in any part of the reservoir for any cell in your model. And you can use that with the parameters of the Brooks-Corey to calculate water saturation in each cell in the model. The beauty of this, like I said, the parameters, don't forget that they are calibrated for each of the rock type that you have there. And also notice that the irreducible water saturation and the entry pressures are themselves related to porosity in this case. They can also be made in such a way that they will be related to the permeability. So it depends. In fact, I prefer when you relate them to the permeability because they help us to really, they help us to be able to avoid when we are creating the bin to change the initial fluid in place. But we can discuss that also in a different section so that we can keep the focus in this recording. We know that the better quality rocks typically have larger pore throats and they will have the lower capillary pressure effect and the lower water saturation at the same height. So when you look at that, and so what you've seen here is the plot on the right showing the resulting capillary pressure curve for the 6 different rock types. So you can see that each rock type behaves differently, reflecting the differences in their pore structure. the flow characteristics, we can see that the higher the quality rock types, the better the lower the capillary effects, and the lower as well the irreducible water saturation that is retained in the rock, basically. And the higher quality rock would drain more efficiently and retain the less water. Unlike if you look at the capillary pressure here, this is a very tight formation with very high interfacial tension or capillary pressure, and also very high irreducible water saturation. From the previous section, we looked at how you can actually generate saturation height functions, parameters from TechLog. So I want you to imagine, in this case, we have the N for each of the 6 rock types that we illustrated in the previous slide. We also have the entry pressure, which are given here, the expression of the parameters, and we have the SWIR, or in some places I can interchangeably call it SWRF, as the case may be, but basically it's the same thing. This is just looking at the asymptotic irreducible water saturation from the numerical curve that we've got while we were building the saturation heights model. Now, what that means is, depending on the source of the capillary pressure data that we're using, if you are using capillary pressure data from mercury injection measurement, this is really prone to error when it comes to the irreducible water saturation, because the measurements can actually go to 0 irreducible water saturation, which is not physical in the reality of the reservoir. But in a situation that you have the porous plate measurement, that can really help you to better understand the irreducible water saturation in each rock type in your model. And that's, if the data is available, that can really be helpful when we are building the saturation height model, as the case may be. But from this point, the irreducible water saturation, it goes on to infinity, right? That is the asymptotic line where the capillary pressures can go on to infinity. But in the transition zone, before it reaches the irreducible water saturation, we have varying water saturation in our model, which can actually be estimated based on the Bruce-Corey expression that we have here. Another set of data that I would like to highlight is, in most cases, you also may have access to the core data with the endpoints. This is definitely not uncommon to have this kind of data in our model. And most of these endpoints, they are really helpful when you are generating your the relative permeability for the model. Now, moving on to the main focus of this section, the approaches that are available when you have water saturation array. There are 2 of them, the SWATINIT approach and the J-function approach. So I'm going to explain the 2 of them. And now you can generate them outside even TechLog. You can use spreadsheet to do that, but you can also, it's more efficient if you have access to a preprocessor like TechLog, but the SCA in TechLog, the SCA plugin in TechLog. Here, this is the saturation height parameters that you have received from your petrophysicist or geomodeler, and you need to make capillary pressure the function of the subject of the formula from this equation. In order to do that, you're going to get this expression and these two equations for relative permeability of water and relative permeability of oil are correlations, which also depend on the endpoints, including SWIR and some of the parameters that we have from the core data. So, and this is a very important integration where we make sure that regardless of the method that we use, whether SWATINIT or J-function, we can actually maintain the consistency between the saturation height model and the saturation function tables that we're going to use in our reservoir simulation model. And once we've computed the relative permeability for the phases present, and we compute the capillary pressure, then we can just generate our tables and use that for simulation. And this can be done for each rock type in our model, as long as we have the parameters. On this slide, I just remind us that if you're also working with the gas oil system, we can definitely do the same, carry out the same calculation. And this is for the oil water system. And I just wanted to pay the attention to the trend as well that we have here. And in some cases, you might have to make a guess of some of the parameters for the gas oil system. But if you really understand the implications of some of these parameters, it will help you to make a better guess of what they're likely going to be. For instance, if I know the entry pressure for the oil water system, I know that due to lower interfacial tension, that the entry pressure for the gas oil system will be lower. So I might find an appropriate factor, which can also be an instrumental parameter to reduce the one that I have in order to be able to make this calculation happen. But what is important is understanding the physics behind it. We know that the gas can invade smaller pore throats more easily, and that is the main implication of this entry pressure, and the reason why it will be lower than that of the oil water system. This second approach, which I'm going to illustrate the two of them shortly, is to use the J-function. And one thing that we need to remember about the J-function, I want you to, based on this equation, whenever you have the different permeability, different porosity, then you are going to need different capillary pressure, okay, basically. But what the J-function is doing is to normalize our capillary pressure curve to obtain a unified function, which can be used for similar rock types. So in this case, I want you to imagine that we have four different porosity, a very tight rock, and a very good rock here with low capillary pressure, low water saturation, good permeability, good porosity, and some other curves intermediate. But if this is similar rock types, we can actually normalize all this and to obtain a unified J-function, which is what you have here. And this J-function can actually be given to the simulator, and the simulator can back calculate the capillary pressure based on the variation in the porosity and the permeability of each cell. This is the data that is not readily available per cell, but which can be calculated from this dimensionless variable. And it could come really handy. And we can use this approach to calculate the capillary pressure from which we estimate the water saturation during the initialization of our module as well. This slide explains the derivation of the Leverett J-function that I just described, which is a way of normalizing the capillary pressure data so that different rock types can be compared on the same basis, as I already explained to you. So this is the capillary pressure equation. And if you try to rearrange this to make a dimensionless nature or setup in this form, and one thing that we'll notice is the R. Of course, we will have a unit of L in the dimensional space, which is the same as maybe meter or something, if you think about that like that. Why permeability has unit of L square? That means that if you find the square root of the permeability, then the units of the permeability and the R will be similar. That means that we can actually substitute square root of K permeability for the R, and we'll still maintain the dimensionalized nature of the relationship that we have here. And even if you move further to divide it by the porosity, it will still not change the dimensionalized nature of this expression. And that is what this Leverett J-function is built on, if you look at it, and that is how we've obtained this expression. That means that if you know the capillary pressure for any saturation point, and based on the interfacial tension cos theta that we've used previously, it can actually calculate capillary pressure also from the J function. So you can also make capillary pressure as the subject of the formula, or in terms of J and the other parameters. So every cell in the model with different porosity and permeability will affect the each, or will result to different capillary behavior, right? If the pore flows are different or the pore geometries are different, then they will expect to have different capillary effects. If you have a very thin pore size, then the capillary effect will be higher than when you have very big pore size. So all this together can actually be incorporated in this powerful Leverett J-function. And besides calculating each capillary pressure for each cell, it helps us to also, we can use this approach to initialize the model, because the moment you know the capillary pressure, you can estimate the water saturation in each cell, which can help us to also obtain the same goal. So on this slide, what you have, I will come back to this in a moment, but I would like to bring home everything that I've been discussing to you by really demonstrating it before we conclude with the last slide. So on this slide, what you have seen here, on the spreadsheet, is actually the implementation of the expression that I've been discussing with you. So I will try to take this off from the presentation mode, so I can put this here so that I can compare the two of them with you very quickly. So if you look at my explanation here, if you have all the parameters, you have the 6 rock types here, and you want to calculate either the capillary pressure or the J function, which is not difficult to make at all. Let's assume that the porosity, the average porosity for the rock type 1 is 0.3, and the permeability based on the expression is that. And for the rock type 1, we have this, for rock type 1, this is the formula here that we're using. And so you can see the value of the SWIR, which is one of the parameters that is needed to calculate the water saturation in our reservoir model. And here you have the N for rock type 1, for rock type 2, you can see up to rock type 6. And you also have the entry pressure, which is this, and which corresponds to this. All these are coming from the petrophysicist, and we have tried to incorporate them here for the first rock type, second rock type, and third rock type. You can use the Corey correlation. One thing that you need to bear in mind is when you are generating the saturation table, you can actually program the Corey correlations, those two equations that I showed you before, this to calculate this and this to calculate this. Once you know those important endpoints. Another easy way to generate that is the fact that you can actually go to Petre, for instance, and you click on make raw physics, and you can put those important endpoints such as the irreducible water saturation or the minimum water saturation, the critical water saturation, let's say for rock type 1. So if you go to rock type 1, for instance, we might just be able to fill in all these parameters as needed. So here, if I'm looking at the rock type 1, I have the minimum water saturation, which is 0.08. And I have the critical, maybe I can estimate this. I might just be able to find a relationship in principle that I can use, but let's say it's slightly higher than this. And that is the saturation above which water becomes mobile. We have the Corey for water, which defines the curvature of the curve. And we know that the smaller the number, the faster the movement of the flow system. And also, the higher the number, the slower the movement. So we also have the Corey here. We also need information around the irreducible oil saturation, which will correspond to, I will show you when we generate the table. So some of the endpoints that you have here are very important, and this is already given to be 0.3531. So 0.3531 when you have it, and maybe it's this is to water and to gas, for instance. And we also have the maximum water saturation, the relative water saturation at irreducible oil saturation, which is this point, which is 0.1217, as the case may be. Then you can define how many table entries that you want. For instance, you can say 20. And if you do that, on the capillary pressure, you might choose not to use capillary pressure from the correlations, because we're going to calculate it and copy it back into Petre. So once you do that, the rock type 1 is already generated. Maybe I should rename it as rock type 1 actually. So you need to repeat for rock type 2, rock type 3. And once you have done that, what you see here is it will generate the 20 entries that you have requested and factor all the points that you've requested. All this also, you can just program it yourself on the Excel. And you see those important points that I mentioned to you that we need to capture. And once you capture that, which should be similar to this, the next thing that you're going to do is to calculate the capillary pressure. So the capillary pressure, usually the first point will be undefined, because it goes really into infinity to high number, but we can always estimate that. But the formula is the same thing as this formula that I've shown you here, which is the entry pressure. And the entry pressure for rock type 1, you already know the value, and into 1 minus SWIF over water saturation minus SWIF. So basically what you have there, this is the SWIF or SWIR, and this is the water saturation point. So these points are really important, especially you want to make sure you have control over this. You have to align it with your data. This is also important. And the rest, you can interpolate between them to get the number of entry points that you want. And from there, you can calculate the Corey relative permeability, then the capillary pressure. Like I said, is strictly based on this, which is all these are coming from the saturation height function parameters that has been given to you by your petrophysicist. And once you put that in, and these are the value, and you need to, don't forget to multiply that with the theta, interfacial tension cos theta back, so that you can take it back to the reservoir condition. And that is what you have seen here, multiplying this by this. And once you finish with that, what I've done is just to copy this point, the saturation function, but that is, you can do it any way that you can do it to copy. And also these ones, I copy them from here, the reservoir to this point. The one that is undefined, I try to just estimate the value that is high enough to give me the right value that is consistent with my reservoir heights. Then I can also estimate the J-function. Don't forget that to estimate the J-function, from what I've explained to us, the J-function is based on this expression. Once you know the capillary pressure, you can divide by the interfacial tension, cos theta, multiplied by the permeability porosity. And we already know the porosity and the permeability, and we already have the capillary pressure, which is here. And so we can use this expression to generate J-function. And you can see for the rock type 1, the J-function is the pink one, the normalized one, and the actual capillary pressure is this. And you can use either of the two in your simulation model. And that is, if you are going to use SWATINIT approach, then I will copy this and use it. If I'm going to use J-function, then I can copy this and use it for my model. So how do we copy that to Petre? So we can just come here and add a line, and you can go back here if you're using capillary pressure function or SWATINIT, and you can just paste this here. And once you paste that, you can add that into your model, which is here, and we've created that. Notice that here I try to uncheck using correlation for capillary pressure, so that the data that we copy would not be overwritten by the Petre process. Okay. And once you have done that, if you also want to use J-function, I can just come here and maybe make a copy of this and convert it to J-function. So maybe let's rename this as rock type 1, but this time around, instead of using capillary pressure, we're using J-function here. Maybe the first one, we can put it as capillary pressure. We have capillary pressure here, PC. And the one with J-function, what you need to do, just convert this to J-function from here, convert this to J-function, but you need to actually copy the data, the J-function data that you've calculated. So what you want to do there is to go here and copy your J-function data that you have computed, and you can plug that in here. So if you reopen that, you will see that your J-function data is here. But the moment you intend to use the J-function, don't forget to create the J-function parameters, like the interfacial tension that you have used in this model. Let's say 30. And the square roots, we use 0.5 for the porosity and permeability term. And for the gas, maybe if we're not really factoring gas into it, but if you have gas also, surface tension, you could add it. And now you've created the J-function parameter. And this can be applied to all the rock types. Here, I've created only for rock type 1, but you need to create rock type 2, rock type 3. In our case, we've got 6 rock types. Okay? Once that is done, the next thing that you want to ensure that you have is to compute all the necessary properties that we have discussed previously. And if you look at what I've done in the calculator here, it's just to calculate the reservoir quality index, which is 0.0314. And I try to use a general template for that. So general. And you can just compute that. And that is what you have seen here. Then you can do for porosity as well, normalized porosity, which is this that you have done. And you can do the same thing for FZI. And once you have done that for FZI that you have in your module, then you can create your SAT norm. The SAT norm is depending on the ranges of your FZI. So you can create your SAT norm for rock type 1, rock type 2. Okay. So each cell now, the good cell, you can see them and different rock types that you've got in your model. Then the next thing that you want to do is to use this to set up your initialization of your model. So if you're going to set up the initialization, let's imagine that I want to do SWATINIT. So to do the SWATINIT, it's important that you add the water saturation array that has been created by the geomodeler using the same models that you have received. So you can just append that here. And once you append that here, you also need to append the relative permeability. In this case, we have 6 saturation or 6 rock types. And these are the 6 rock types that we've computed based on the FZI cutoff points that we've been given. So I've already done the relative permeability for rock type 1. Imagine you need to do the same for rock type 2, rock type 3, rock type 4, and 4 and 5. So once you have done that, then you can launch that. One thing that is important here to highlight is if you drop the SWI, make sure you select water saturation PC scaling. That's the SWATINIT approach, basically. And we can convert this to J-function approach. And the difference that you're going to have if you're going to use J-function approach, for J-function, the main difference is you will need to take this out. It will not be necessary again because the water saturation will be calculated from the J-function, from the capillary pressure. So you're going to append this where you are using the J-function that we've copied. So you can now append it. Then if you do this, you can see that it's requesting for the J-function parameters, which is this that you have created. So you can add the J-function parameters to your model. Each one for each rock type, basically, and immediately everything is okay. So this is the approach, and you don't want to mix these 2 approaches together. Once you compute this, the last thing that you need to check, the last thing that you will need to check is to validate your volume in place. So you need to compare the static and the dynamic volume. The static model, that is coming from the geomodeler, and you need to compare that at different levels, the zone level, the field level, the segment levels, within the tolerance that has been agreed upon, right? If it is less than 1% or 5%, depending on the size of the fluid that you have in the system. So once you have done that, you run the case, and if you are not matching make sure that other parameters are the same. If you deactivate any cell in the dynamic module, make sure the same cells are deactivated. There is alignment between you and the geomodeling team. And if the B or the formation volume factors that you are using must be the same. If all the factors are the same geometry, the same porosity, the same fluid properties, then you can adjust the bin size, maybe for the porosity or permeability, depending on what you're using. What does that mean? If you look at each rock type, let's say I've assigned only single porosity, and if I'm not matching within a particular rock type, I can increase the number of, I can divide the whole porosity range into maybe 2, 3, or 4, and find the average of each one. Then I have to generate the relative permeability for each one using my spreadsheets that I've got. So for instance, I have to go back if it is 0.31. For the moment you enter the number, everything will automatically be adjusted to the porosity, because the whole equations, they are connected, all the equations, and they will help you to regenerate this, and you can copy and use it for each of the bin to improve the accuracy of your in-place volume. So once you generate the PC for each bin, then you also have to update your StatNum, because now you are saying that the cells that will use different relative permeability curve that you have created, different capillary, is based on their range of porosity, that if within a particular rock type, if the porosity range is between so and so, use this J-function or use this capillary pressure relative permeability data, and so on and so forth. So that is why you need to update this. And if you run it again, you will see that you will be able to match within the acceptable tolerance. So with that, we've come to the end of this section, and I want to say a big thank you to everyone. Don't forget that 2 approaches that we've discussed today. Either you use J-function, whereby you wouldn't need to append the water saturation array, or the parameters of the J-function, they are already reflecting the Brusco parameters that you have used, or even the J-function parameters, depending on how the water saturation array has been modeled for you. Then also the SWATINIT approach, where you really need to append the water saturation and provide the capillary pressures that will be scaled to match the water saturation, initial water saturation that you have provided. And that's which is this. And like I said, if you try to mix them together, the system will default to SWATINIT. So you wouldn't want to do that. So I want to say a big thank you to you for your time, for listening, and I will see you in the next recording.